Hello, this video is on a new variable called momentum and the concept of conservation of momentum, which fits into our conservation unit. The essential question is, what is momentum and how do we use conservation of momentum to make predictions about objects in a system? So we are going to use the letter P to represent momentum. Why P? I don't really know. I mean, I think they used up M for mass already, and so they were looking for something different, and the Latin word for momentum has to do with a P or something. But anyway, we use the capital letter P to represent momentum in physics. Momentum is defined as the product, which means multiplied together, of an object's mass and its velocity. But kind of a colloquial or an easy way to think about this is that the bigger the momentum of an object, the harder it would be to bring that object to a stop. The sign of the momentum, whether it's positive or negative, only tells you which direction the object is moving, not whether it has a lot or a little. So it can have a lot of positive or a lot of negative, and both of those would be hard objects to bring to a stop. Just like what we talked about with velocity, the sign of the momentum just tells you which way it's moving. Incidentally, if an object is at rest, no matter what it is, it's going to have zero momentum. The typical units of momentum are the kilogram meters every second, which is a weird, complicated unit. We write it kgm over s, and you will see when we do some calculations where that unit comes from. So the equation that we're going to be using for momentum comes from two mathematical relationships. And we can figure out these mathematical relationships if we think about a series of kind of thought experiments of what object would be harder to bring to a stop. So we have object number one. This is the world female cycling speed record holder who has a mass of about 95 kilograms and at her fastest was going at a velocity of 147 miles every hour. And this is a Bugatti Veyron, which has a mass of 1990 kilograms and also can go at 147 miles every hour. So which one of those things would be harder to bring to a stop? Well, it would be a bummer to be hit by that cycler, but it would be more of a bummer to be hit by the Bugatti Veyron. It'd be much harder to stop that. So hopefully that leads you to the conclusion that mass has a linear relationship with momentum. The more mass we have, the more momentum we're going to have as well. So here's a second thought experiment for momentum relationship number two. Which of these two objects would be harder to bring to a stop? This is Jerome Bettis. He is a football player from my era, known as the Bus, and he was a running back that was really amazing in the league. And so the first object is Jerome Bettis walking towards you. He has a mass of about 120 kilograms and a velocity when he's walking at 1 meter per second. This object is also Jerome Bettis, but now he's running. So this is Jerome Bettis, same mass, but his velocity is 9 meters every second. Which one of those two people would be harder to bring to a stop? Hopefully you realize Jerome Bettis number two, which brings us to the conclusion that velocity also has a linear relationship. The more velocity you have, the more momentum you're going to have as well. So the equation for momentum with these two linear relationships represented is P equals M times V, or P equals MV. So it's a pretty straightforward equation. It's the first equation we've learned in this class. And it's a pretty easy one to actually apply. I'll do a sample problem here in a minute. So here's a really quick and simple sample problem. What is your average momentum when you are walking? Well, let's assume you have a mass of 80 kilograms and a velocity of 2 meters every second. We're going to plug it right into that equation that we just learned on the last slide. P, or momentum, equals my mass, which is 80, multiplied by my velocity, which is 2 meters every second. And you get the result of 160 kilograms meters per second of momentum. It's also useful to be able to think about momentum conceptually sometimes. So I've made this table here where we have the mass of an object on the top and the velocity of objects on the side to give some examples of objects that would have a lot or a little momentum. So an object with a lot of mass and a lot of velocity would be something like an airplane flying. An object with a small mass but a large velocity would be something like a bullet flying. A large mass and a small velocity would be like an elephant walking. A small mass and a small velocity could be a beetle crawling. A large mass with zero velocity, a good example is our universe, which obviously has a ton of mass and has no overall velocity, the universe itself. And an object with a small mass with zero velocity would be a pebble or something at rest. you'll notice that these objects have been kind of color-coded to match up with kind of rough scales of an amount of momentum. That airplane is a high momentum object because it has both a high mass and a large velocity. The bullet and the elephant are in the medium momentum category because one of the variables is very big and the other one is very small, so it kind of cancels each other out, or doesn't cancel each other out, but it averages each other out, and we end up with sort of medium amounts of momentum. On the low end of momentum, we've got our beetle crawling, which is going to have a small amount of momentum because it has a very small velocity and a small mass. And then, interestingly, the universe and the pebble have exactly the same amount of momentum, even though one of those is a huge object and one is tiny. But because they have zero velocity, they actually have no momentum, or zero momentum. So they actually have the same. So how could you use the idea of conservation of momentum to solve a problem in a closed system? Well, here's an example of a type of problem you might be interested in. It's a collision between a pool ball, or the cue ball here, and a whole bunch of pool balls on a table. If you've ever played billiards or pool, that's what the system looks like as that cue ball is on its way. And then that next one is what do all the balls look like about 1 second later after the cue ball has hit. So if you wanted to analyze this from a momentum perspective, you could calculate the momentum of that cue ball, and it would have definitely some momentum because it has mass and it has velocity. I didn't give you the mass and velocity values, but let's just assume that you multiplied them together and we got a total momentum of 10 kilogram meters per second of momentum, which is reasonable. The other 15 balls sitting there at rest have a total of 0 kilograms meters per second of momentum because they're not moving. So you can add up all those zeros. But when you are interested in this conservation as a system, you have to consider everything in the whole system. So we got to add together the 10 plus 15 zeros, and you can come up with a sigma p, or a total momentum in this system, of 10 kilograms meters every second. Now, because momentum is a conserved variable, that whatever momentum was in the system a second ago, the same momentum has to exist in the system at every moment in time in the future. So when we look at these balls as they're all splitting everywhere in the table, you could figure out the momentum of each one of those balls. And some of them might have positive momentum and some of them might have negative momentum all over the place. Some are moving really fast, some are moving really slow, some might be stopped, all sorts of directions. But one thing that physics says is that if you add up all those values, and you can do it if you don't trust me, but you add them all up, sigma p is going to be 10 kilograms meters per second at any moment of time, because momentum in the universe is conserved. So this is a complicated example. The lab that you guys will be doing involves more simple examples with just a few objects colliding, but the same truth is going to hold. Total momentum in the system is going to be conserved. Okay, we've come to the end of the video, so take a moment to summarize. Please revisit that essential question, see if you've had any insights or questions about it, and record your answer in your notes. Thanks for watching.